Okay, so this is the final video in section 7.4, which has to do with arc length. There's one other topic in this section, and that is not just arc length, but surface area. So we already did solids of revolution, and that was more of not an area issue, but a volume issue. So in this chapter, you can see you have all three dimensions. You have some length problems like we just did, you have solids of revolution, which are volume problems, and you're also going to have kind of like shell problems, if you will, which have to do with the area of a surface of revolution. So the idea here is that we've got some kind of surface of revolution. Okay, so I really liked their pictures in the book. So you can notice that this is not solid. Don't be tempted to think that this is what we had before when we were considering it as a solid of revolution and we had like um, disks of infinite thickness, and then we considered the volume of those disks by calling like this dimension dx. That's not what we're doing in this section. In this section we're thinking about, well, what if we just need the area on kind of the outside of those disks, if you will. Alright, so the lateral surface area of a real simple shape like this guy, this is called a frustrum. The lateral area, or excuse me, the surface area of a shape like that, if you're just thinking about the lateral part, not the two circles on the end, then you'd have to go plus. If you wanted the total surface area, I guess you'd have to go plus 2 pi r squared. Right, but we're just thinking the lateral area, that's what we're going to have for our surfaces. The lateral area, if you unfolded that, right, like the edges out here at the edge length is going to be the length of this circle's edge, which is otherwise known as the circumference, which of course you guys know is 2 pi r from geometry and whatever else you've had. So you do 2 pi r and then you multiply by this dimension if you unfolded it, and you get the lateral area of that surface. So we're going to be seeing that this basically just becomes some kind of integral in order to do this for any arbitrary surface. For times when this guy might not be a straight line. Of course, most functions don't have that. What if we have some kind of function that's not a straight line here? What if it's like some kind of weird polynomial function? And we want to think about the surface area from here to here if we spin it around the x-axis or something. Okay, so notice they picked the x-axis as the axis of revolution on this one. It doesn't have to be, though. So you'll see this is pretty similar to stuff we've already done with arc length. Anyway, so first you've got to consider that function. So here's like the function's arc. So I don't think you should really go through this derivation again. Remember, I taped the derivation for how the arc length went, but you can see that looks exactly like the same kind of thing that we did when we did arc length. You had to introduce that clever one, factor out the delta x sub I squared, and then the square root of something squared, it pops outside the square root right there. So this is the exact same thing we did for arc length, right? Because this is the arc length. That's equivalent to what we had up here with the L, the length right there. Okay? I'm going to erase some of this stuff in case we need to come back. Holy. Okay. So that whole part is just the same thing that we did it for arc length. Then this part, this 2 pi f sub d sub I, f of d sub I, that's just 2 pi r. F of d sub I is being picked within each x sub I to x sub I minus 1 subinterval. Basically, just think about it as d sub I is a point that exists. It's guaranteed by the intermediate value theorem. So, I mean, if you did this on a higher level, this is definitely a proof. It's guaranteed to exist on each little subinterval. And if you do 2 pi times f of that value, well, f of that value is this distance, right? If d sub I was for right here, for instance, on that subinterval. And then that gives you this part of it, the length of this curve. And you multiply that length times this length, and you integrate that, or you add it all up, and that's basically going to be the surface area. So let's look at the details a little bit more so you can see that they're adding that all up. You can see the 2 pi is constant, so it was factored outside of the sum. And this part, I think the only thing you can possibly really mess up on this is that this part has to stay inside the sum. Why is that? Because it's variable, right? If you think about the curve back here, sometimes d sub I, f of d sub I is this long, sometimes f of d sub I is this long, sometimes it's really short in here. It's variable. So it cannot be factored out. It's still inside the sum, and then this is what we had for arc length. If we take the limit as delta x sub I goes to 0, right there, then you get the integral. So that's pretty much it. So the surface area, this is capital S, right? I don't like that they use S in both, so I'm going to write a great big S. In fact, you know what? On your problems, what you might do to clarify is just call this surface area. That's probably smarter on your problems. Okay, so anyway, that's just going to be 2 pi outside the integral from wherever you want to start to wherever you want to stop on the curve, and then f of x, and then the arc length part, right? 1 plus f prime of x, make sure you get it the right way, squared dx. So this is almost like arc length, except the only new parts are you've got 2 pi outside the integral, and r, the radius, has to stay inside the integral because it's a function of x. Okay, you can do this in terms of the y-axis or the x-axis. It really doesn't matter. So you could do this where f of x is some radius as a function of x, or it could be a radius of some function of y, and then this part would have to be dy. Okay? So, not hard stuff. Let's do one example, and that should be good. So it says, think about x cubed, find the area formed by revolving that graph about the x-axis. They could have asked about the y-axis. Make sure you watch your axis of revolution. And they said do it from 0 to 1. So you can see that there's hardly any area accumulating in there. But once you get out to here, it's spreading out a lot, so you get lots of area on that outside surface. Remember, this is not a solid. So we've got the arc length part right here, right? We've got 2 pi r. Oh my gosh, that's just terribly sloppy. I guess I'll just underline it. So we've got 2 pi r in here, so we need to think about what's the radius. I like the way they've drawn it. The radius is this part, so it's the function value in this case. Sometimes you might have to alter it a little bit though, okay? So the function value is just y equals x cubed. So you do that. I don't know what else there is to say about it. So notice they've squared that inside. Let's see, have they done anything else? So they took, the derivative was 3x squared. They squared that to get 9x to the 4th. They rewrote it as 1/2. What are they doing here? I wonder. Isn't that just from like a u sub? They're not really stating it, but the u sub is u is the inside 1 plus 9x to the 4th. Du then is going to be 36x to the 3rd. And they said, hey, look at that. They kind of always do the u subs as like a clever one, don't they? The way we do it is we go like this, and then we say, hey, put that 36 right there. And then you have your x cubed right here. Anyway, so it comes out to this integral, and that comes out to 3.563. Make sure you get your units on here. Even if they don't give you units in the problem, this is square units because we're talking about the surface area on the outside of this tan shape, right? It's not filling it up with volume. Okay, hope you found this useful.